Okay, you know, like I said before, you always design, around any part, whether you're doing 3D printing or not, and you're designing any kind of apparatus or enclosure or anything, you always design around your constraints, the things that you can't change. And this tube is one of the things I can't change. Um, so because of that, we're going to start by designing around that, so I'll start with that little ring I was talking about. Because while I could go buy other tubes, through U.S. Plastics or somebody like that, they have a pretty good selection of plastic tubes. That's still an additional expense, and I have to wait, a week or two, and you know, um, and so forth. And I just want to use what I have on hand because this is just a proof of concept. I'm just trying to, see if this is a neat little product or not, if it's worth going further with at some point. Or not, because I don't know, and that's what's nice about a 3D printer, is you can do investigations like this, and try to tweak your design and form before you even worry about whether it's manufacturable or not. It's what they call a proof of concept, or POC. As opposed to a prototype, which is a prototype is usually when you've already looked at the proof of concept and are actually on the road to actually trying to create a real product. That's how I differentiate a proof of concept, or POC, from a prototype. So, and you got various stages of prototyping too, by the way, typically. Um, from, initial prototypes clear up through, um, to design and development prototypes, clear up to, pre-production prototypes. Um, so they get more advanced, depending on how many stages you actually need to do. Um, but in any event, the point is we're just trying to do a proof of concept here, so I want to use what I have on hand just for convenience, and to keep the cost down and everything like that, and to move along with this thing. Um, but anyway, this tube actually represents a primary constraint for the housing itself. So we're going to go ahead and start with that, and with the slip ring. That's going to be the basis of our design, and that's what you always try to do. Is you try to look at the immutable parts and of your design anytime you're starting a design, and try to make adjustments. I mean, look at the batch of immutable parts to see which ones are going to be principal design constraints. That's always the best place to start, like here, because otherwise it's sort of arbitrary. If we didn't have this constraint here, it's arbitrary. If we didn't have this constraint, then the only constraint we'd have is the size of the battery holder, which I can't change because I'm not willing to do my own custom battery holder. That's just too big of a pain in the butt. And the switches, these are the two things that do affect the design parameter, the design form of this thing a little bit, to one degree or another. Because of this, we can't make the housing too skinny, for example. We can make it as wide as we want, but we can't make it too skinny. Because of these, this also dictates, how skinny we can make it, because, frankly, if we tried putting like two switches like this in a tube like this, let's say that was the outer housing. Well, we couldn't fit that thing in there very well, and let alone two of them. And even if we could, that switch might barely stick out of there, because remember, we've got to have some wall thickness and so forth we got to account for. So we couldn't actually take that tube right to the end, because there's got to be some material between the corner of this switch and the wall. Plus, we got to have allowances to actually accommodate that, particularly given that the 3D printer, again, we got to, at least have like a 25 mil allowance around this thing, if not better than that, so it doesn't fit too snug, because otherwise we got to go in and try to file it down, and that's not good. I could actually print my 3D printer, at a higher resolution setting, and go tweak it even and get it closer to reality. But in practice, it's usually a good idea to try to design around loose tolerances, particularly if you've never taken your product to a production run before in plastic. Because you do not, imagine if you went and spent $20,000, okay, tooling this part, and it was based on a switch that you had too tight of a well here, or accommodations for the switch. Well, you might have to spend another $20,000 to make it wider because the switches don't fit. That's why it's better to have too loose of a tolerance usually than too tight of a tolerance. But it just depends on your product too, because sometimes you can't get away with that depending on what you're doing. If you're doing a lot of gears and stuff, you wouldn't want too light of tolerance because then the things wouldn't mesh. And in that case, you're going to have to do a lot of precision. But we're not doing things like that here, so because if I was doing like a series of plastic gears that had to mesh that we're going to eventually injection mold, I would have to tweak my printer to try to get it as precise as possible so that it matches the tolerances of whatever plastics company I was going to use, what tolerances they can maintain for an injection molded part. That would require a lot of additional research and so forth, to make sure things are going to come out right. And that's where it gets really tricky. And if you're doing that kind of design, I'd advise you to think about it, and see if there are ways you can do it completely differently than what you're considering, because that's a big risk to take, because you could spend gobs of money and have to do it over and over and over again. If you're trying to make something that has to be critically sized, and 3D printers can help you to some extent, especially when you dial them in, but there's still always going to be some error in it, and between that and its precision and what you're going to get out of the plastics company. And that's when you have to start printing parts with a tweaked printer and then keep adjusting your size and so forth to where the actual printed part comes out to what the theoretical tolerances will be from the plastics company. So it gets real tricky, and plastics too, you got to understand that when they injection mold parts, sometimes they don't always shrink uniformly. So you may have, that's why usually the practice is to keep your wall thicknesses all the same, because when plastics cool, they typically contract a little bit, and when they do, some of their wall thicknesses are going to change a little differently than others. So there's a little bit of an art to it. Now, if you're ever doing extruded plastics as opposed to injection molded plastic, it's really an art. That's more of an art than a science, doing the molding around that. So and I've designed around lots of extrusions in my time, done lots of plastics extrusions in my time, and aluminum extrusions, as you'll see in some of my other video clips. But the fact of the matter is that if you do extruded parts, it really is fly by the seat of your pants. Just trying to get something close to accuracy is something that's accurate is pretty tough when you're doing extruded parts. But injection molding is a lot more accurate, but there's still going to be some some little quirks to it. So again, if you're needing high precision, you're going to have a lot of research on your hands trying to make your 3D printed part simulate the precision you're going to get out of a injection molded part, and in the end you're going to end up having a design that looks different than the design you're going to have to send to the manufacturer. So you're going to have certain, an injection molded design, and then versus a 3D printed design where the dimensions of everything have been tweaked, to try to get as close to the final theoretical output product, that you can, with 3D printing, and just to make sure everything works. But even then, you may think you got everything dialed in, and you may send that tooling off, pay that 50 grand or whatever, and then find out that parts still don't work right. So that's the thing. That's why I'd advise you, if you're new to plastics, if you're not a real mechanical engineer, and you're new to plastics, I really advise you to rethink the way you want to do things. And it may even pay to do a design and use software that's parametric, not like Rhino. That's the thing about Rhino that's bad, is it's not a parametric package. So if you want to make a change in a part, usually you have to go redraw the whole part. So but I was going to say, if you had a parametric package, you could actually hire like a mechanical engineer that has plastics experience to review your design, and maybe even the manufacturer will do that for you. But again, they still don't know your design intent, so you're probably going to have to pay somebody to look it over. But if you're looking at spending 50 grand on tooling, versus and the prospect of having to dish that money out again and again while you tweak your own design, it may be better to pay some mechanical engineer 5 grand and have them look your stuff over if they've got experience with this kind of thing. And so you only have to do that once. So that's something to take into account. It's either you know, if you're going to do something that absolutely has to have precision, you know, like I said, a gear train or something like that, you know, for your little product. Because remember, I mean, you're probably going to be making it out of different plastic too than PLA, so there's, you know, mechanical factors too, like strength and abrasion resistance and so forth. And I know you can 3D print out of nylon, but I still don't know if that's the same grade of nylon as you'd use, like, if, for example, if you wanted to make a gear train. A lot of gears are made out of various grades of nylon, you know, and they wear really well. They don't chatter as much. But the point is, you know, gears are a great example of, the reason I'm talking about it is they're a great example of something that's high precision, you know, and you're going to have a hard time duplicating, you know, gears, especially if they're small gears, you know, like, you know, double helical gears or something like that. You're going to have a hard time simulating that with 3D print to begin with accurately, just because the precision of 3D printers just isn't that great. You might want to go get you a stereolithography printer, which those have, you know, 3D printer, which is, those have come down to a few $1,000s or so, and they have a lot better precision than these, you know, fused layer deposition printers like the Robo 3D that I have. But again, you know, it's a bigger budget. It just depends on what you're doing, you know. But if you're doing something high precision, it makes sense to have as high precision printers you can get, because you're going to have better results, you know, gears that mesh properly as opposed to fused layer deposition. Even with a dialed in printer, you're still only going to get that so accurate, you know, if you're doing anything that precise. But you're talking a higher dollar printer there, you know, than the $800 3D printer I bought, you know, for this kind of thing. But I'm not planning on doing anything like that, and if I were, I'd try to come up with a way of not having to have a gear train if at all possible. For example, if I had a design that needed something high precision in it. But the best thing to do is to make sure you leave tolerances, which is what I like about 3D printing, especially with an undialed in printer, is it almost forces you to leave loose tolerances in it. You know, which again, if you keep that in perspective and realize what loose tolerances could do to you, you know, to your final design, whether it'll be critical or not, you know, it's usually a good thing to have those loose tolerances in it. But sometimes there is such a thing as having too loose of a tolerance. But, you know, you got to keep that in perspective with whatever you're doing with your design. In fact, a lot of the designs I, you know, did may need some minor adjustment, you know, for a you know, for an injection molded part, keeping the tolerances into perspective, you know, on 3D printing versus what I know they can do and what they can safely hold, from an injection molded plastics company's perspective. So the fact of the matter is, though, is that's kind of why I like 3D printing, because it does have that, you know, it does have that, you know, force you to work, you know, especially with an undialed in printer, it forces you to work with looser tolerances, which usually will work better for you. You know, like the switch well, it wouldn't kill us if we had a switch well surrounding this, and by switch well I mean a switch capture, you know, which I'll try to show you a picture of here during this episode. Yeah, and if you like I said, if you edit, you know, this is where I'm going to inject a picture of a switch well from the 3D candle. But yeah, you know, here's an example of a switch well, and you can see that, you know, that you know, on some of the parts I did, that, you know, that actually allows a switch to lie in there. Anyway, I'll just do this as a separate video, a separate little video clip on the subject if necessary. But anyway, switch well, you know, is something that, you know, will actually capture the switch, so you can't move side to side, you know, side to side or anything. You know, basically captures the switch. And sometimes you need to do things like that. This is just a great little example. But if you had too loose of a switch well, that's not going to necessarily kill you in design. It might mean there's a little extra play in your circuit board, but honestly, I'd rather have a switch well that was too loose in my first production run of plastics than a switch well that was too tight and I couldn't fit the switch into it. Because at least if it's too loose, hell, I can inject some, you know, stick some, you know, a little bit of epoxy or something like that, rubber cement or what have you in that switch weld to prevent it from doing that. You know, it's a little extra of a production step, and but on the other hand, at least you don't have to redo, you know, $20,000 or $30,000 worth of tooling, you know, on it. So the point is, when you're doing your very first production run, it's good to have loose designs, not too tight of designs, whenever you can manage it, because you know what you want to do is, if you invest a bunch of money in tooling, you know, you want to make sure, you know, that you don't have to do that again if at all possible. Yeah, it may require some extra steps, you know, to try to get your first production orders out. But on the other hand, at least you don't have to redo all the tooling. So it may cost you a little bit more money in initial production, but again, once you get the, you know, get your profits up and everything else, you can redo the tooling and get it right. When you can afford to redo the tooling and get it right, you know, that's what I'm trying to say, and that's why that's a good, you know, practice, you know, when it comes to 3D printing, and getting a business started up. You know, it's based around parts that are, you know, plastic parts that you're going to have somebody, you know, tool up and produce for you, and you do the assembly of. You know, it's just better to make sure you cover your butt on that, you know, by making sure your initial parts, you know, have loose tolerances and that they will fit, just maybe loosely, but there are ways around that, you know, using, you know, tape, or, you know, like I said, epoxies or whatnot to make up for the difference if it becomes a big issue. So again, better to be a little too loose than too tight, you know, because too tight, trying to machine plastics, and most injection moldable plastics are all thermoplastics, you know, and given that fact, they usually don't tool or machine well, which means that trying to have somebody go fix it for you is going to be really difficult, to say the least. You know, it almost mandates that you go and redesign the part and retool it, you know, to try to correct that flaw in it. Whereas if you make the tolerances too loose, you know, if your design will tolerate that, well, you're better off, you know, with your first production run being a little too loose than a little too tight. Just always, because otherwise you're stuck with a batch of useless parts, you know, even though it was just a test batch, you know, that they did, but you're going to have to redo the tooling, and that's what's going to get you. But never, ever, ever, ever have a plastic part made and also place a production order for it at the same time. Never, ever, ever do that. You know, that's the #1 no-no. Always have your, you know, pay them the tooling fees and let them do a small production batch, because they always do a test run when they develop tooling. And they'll always send you however many parts you request, you know, for that production, you know, that small test run. You know, if you're doing extruded plastics, you know, don't be shy to request, you know, 100 feet of it or whatever. You know, if you're doing injection molded parts, you know, say a couple hundred pieces. You know, you'll pay a little higher of a price, but it is a test run, so it's not going to cost you that much, really, in the greater scheme of things. But you definitely want to get enough pieces in where you can actually run some tests on them and make sure everything's kosher. To make sure you don't have to redesign the tooling. But it'd be a disaster, you know, if you had an injection molded part made, you know, you spent $50,000 in the tooling, and then also decided to go ahead and order 50,000 of them while you're at it, you know, without actually, you know, reviewing the first article off that. You know, that never ever do that. Always, you know, it takes more time, but always have them do the tooling, send you the samples before you give a go-ahead to go into production. You know, but never get that impatient, because believe me, that could bite you in the ass. Because it's still better, if you're going to have to redo the tooling, it's better to just have to redo the tooling, not redoing the tooling and a production run. So, you know, that's just common sense. You know, don't ever break that rule. But at any rate, on this, like I said, we'll go ahead and start with the ring, and we'll go from there. may take some of these clips too and actually put them in a separate little video, you know, like design tips, you know, to separate it out from, you know, from the actual design process here. Okay, but on this ring, you know, the principal constraint here is actually this inner wall. So let me go ahead and move, well, go ahead and move this down to the base here so we can kind of work. Okay, well, like I said, the inner wall here. Now what I'm going to need, you know, because like I said, we're going to have this little guide ring that this piece attaches to, but it's going to attach by glue. So and this little guide ring will actually be pretty close to the actual cylinder wall. So I don't want glue, you know, because in order to assemble this thing, you know, I've debated about that a lot. I've actually got to, you know, attach our guide ring that we're about to design to the housing and glue the housing all together first, and then glue this tube onto it after the fact. That's the only way I can really conceive of assembling this thing after fashion, just so I can get to everything properly. So what that means is I'm going to be applying glue to a ring that's on a, you know, plastic ring that's on a 3D printed plastic ring that's already around a 3D printed plastic case. I do not want glue seeping off into that and gluing the ring to the plastic case. So what I need is a little wall here that will prevent glue from seeping near the cylinder. And now that wall's got to have some tolerance, because, you know, a tolerance for error in it, because remember, 3D printer, you know, has got that tolerance for error. So I got to come in with at least you know, a 22 mil inset. So that would have to be the wall, because again, that'll probably be quite snug with it. It's going to have to be a thin wall though, because I don't want there being a great deal of distance between this tube in general and the plastic housing. So I'm going to want to keep this wall thick, certainly way less than a 1/16 of an inch. So say about 0.037, I'm just going to arbitrarily say, just as thin as I think I can get away with on 3D printing, because like I said, I could probably go thinner than that. I don't want to make it too thin though. I'm going to go ahead and go with 0.03. Okay, so that will be the inner wall of the tubing, I mean of the ring. Now on top of that, we got the inner wall, the actual housing itself, which I'm going to allow at least 25 mil. In fact, I want, you know, because again, it's got to be loose enough to where this thing's going to be able to slip around it. So, you know, I'm probably going to want to put that at like at least a 30 mil tolerance. So that'll give us a total of 60 mil around, you know, around the, you know, because it's 30 mil on this side and 30 mil on the other side too. So it's 30 mil on both sides, total 60 mil. That should be loose enough, because I you know, we want this too to be able to easily slip up and down the you know, the housing itself without getting bound up. So anyway, you know, you can see how the constraint of this tube actually ultimately dictates where how big our inner our outer wall of our housing can be. So, you know, these two here that's the wall of the ring. Now the outer wall of our slip ring can be this. So let me take a line and do a measurement on it. So that means it'll be, you know, 111 mil, which you can see right down here, how long the line is. So make sure it's not saying center, but yeah, it's 111 mil. That's almost an eighth of an inch, you know, which is an eighth of an inch, 125 mil. So that's an adequate thickness. So basically, what I'm going to do is I'm going to grab this curve and this curve here and extrude this out. Now, I want this thing, this little ring, I don't want to get carried away with it. And again, watch this down here. That tells us how long the extrusion is. So that's an eighth of an inch right there, you know. But I probably want it a little more than an eighth of an inch because I got to put some guides in it. So I'm going to say minus 0.165, let's say. It's rather arbitrary. A lot of the stuff is kind of arbitrary, and again, it's a proof of concept, but this isn't not a principal constraint. A lot of these measurements I come up with just out of instinct too, by the way, so you got to keep that in mind. Anyway, that's got our ring right there, okay? And I used a minus because that's just a quirk of Rhino. Minus made it extrude down, plus would make it extrude up. So when I put a minus 0.165, 165 mil. Okay, but now that we got that in, I can take this curve here and this curve here, and we can extrude. And it's advisable sometimes when you're doing, well, we'll just try it this way and see if it works. I'd like this to be at least, say 0.15, and notice I didn't put the minus sign in it that time, so extrude it up and you can see what we did there. So then I want to take these two parts and try to union them. Okay, so bingo, now they're one part. So I did a Boolean union on them, so we got our ring. So this tube, will actually sit right in there, so I can apply glue, down there when this thing's already on the device, and then I don't have to worry about the glue leaking out into the, getting stuck to the housing, so that it fixes the thing in place. Now the other thing we're going to need is 3 guides. So I'm going to use the rule of 3s on this, because we're going to have actually 3 tiers of LEDs, which I haven't gotten to lay those out yet because I was trying to figure out the tubing. But now that we know that our tube is going to be, our housing tube is going to be no smaller or no larger than this, I can actually look at laying out the LEDs now. So I'll go ahead and do that before I do anything else. Let me just delete that, and just gonna move this sucker and put it at origin. This is why I always try to work with 0, 0 too on the origin, so I can always use 0. When I'm entering things in here, sometimes I can use 0, 0, and I always put it at the the origin of our working plane. And then I'll move things from there. And this is sort of arbitrary at this stage where I put it. But for this design, see, we don't want to come too close to the ends. In fact, we want it to be about right there. I'm just kind of guessing, but again, that's the whole point of prototypes. I don't want it to come too close to the end because these LEDs are 55-degree LEDs, so they'll have a cone to them. Which I've actually drawn a cone. That's one of the nice things about in CAD. You can actually draw a cone with a 55-degree angle on it and kind of see what's going on with it. But you want to keep it a little bit close, a little bit far away from the edges, and try to center it a little bit. But I don't want to get it too close to the middle either. And you'll see why later, when I start drilling holes in this little diffuser here, because you'll see why I'm doing this later. It's because I don't want light to peek through the holes too much. So there's a little bit of a compromise. A lot of engineering and design is about compromise. Let me copy this because this is actually going to be, I want to keep these things pretty close together. And again, we're probably going to have to move them still. But there's going to be a total of 6 LEDs in this. So 360. So that's basically sort of what we're, targeting here LED wise. Now again, I'm going to have to take another look at this in the future to make adjustments on this, because I'm still wondering about the cone. But see, it's actually not that big of a deal now that I think about it, because see, basically 3 of these LEDs, when it's in an LED candle mode, it's only going to use 3 LEDs typically, and when it's in flashlight mode, there'll be one setting on the switch, and that's when all 6 LEDs will come on at full power basically. But when it's in flashlight mode, the diffuser lid will actually be retracted around the LEDs, so you won't really have to worry about it. Whereas when it's in candle mode, normally it'll just be the center LEDs that are actually shining up and reflecting off that diffuser, so that keeps them nice and centered. So therefore, I might be able to actually move these things out a little bit. So let me go ahead and do that. And again, that's why I'm making this video, so you can see some of the decision making that goes in to actually doing a design. You may find it a little boring, but you can learn some things out of this if you've never designed anything like before, period. Okay. But before I do, let's look at one little issue here, and that's the wall thickness. Let's provide for say 125 mil wall thickness on it. Now chances are it's going to have to be thicker than that because of the threads we're going to put in, but then again, the threads could be at a it remains to be seen how I'm actually going to do the threads right now. So I'm going to make an assumption about that. And if it's 125 mil though, that means I can't get the LEDs any further out than that, because that means the inner wall is going to be a bit of a constraint there. So I guess I'm kind of stuck with this layout. So I've answered my own question, because I was going to try to see if I could move the LEDs even further out, again, to get this LED further away from the center than it is, but I can't do that. Okay, so let's just go ahead and repeat what I did before then, because it looks like we're basically stuck with that arrangement, so that's okay. But I don't want these LEDs too close to each other, because when I do the routing of the acrylic, I don't want this piece breaking. So I'm probably going to have to separate these out a little more. So something like that, and that gives us, because acrylic's rather brittle, so I don't have a whole bunch of this stuff, so I want to make sure I don't squander it. 84 mil should be enough. You can see down there, 84 mil should be enough. That's the 1.5/16 or so. Again, I wish this weren't so close to the middle, because in fact, I'll show you why here, if this really is going to be the final deal. I mean, I can always redraw the diffuser if I need to, so let me kind of show you what I'm doing here so you're a little less confused. I'll go ahead and bring this up here. Okay, now let me go draw some tubes here so I can cut holes in that diffuser. Okay, it's from the center. Now this is the inner wall of the LED, so it's about 200 mil, but make it about 220. I'm going to make it about 225. Actually, I'm going to make this, because like the outer wall is 250. Yeah, I'm going to make it about 225. Okay. Because remember, I got to take into account the error in the 3D printer. And if I had to drill these holes out a little more, I could. I mean, I've had to do that once or twice by making them too tight, but I don't want them so loose that the, because you can see on this LED there's this little lip, and it's nice if that lip doesn't slip through the hole, because that, of course on this it doesn't really matter though. Yeah, that's right. On the diffuser it doesn't really matter. The hole can be a little bigger. Now for the when I'm actually drilling a hole in the housing for the LEDs to peek through, that's when I'm going to want to use a hole that's like 225 mil. But for the diffuser, for the diffuser, that hole can be bigger because it's not holding the LEDs into the housing or anything. So, doggone it. So I can actually, oversize the hole a little bit like that, but I don't want to get carried away with it, and you'll see why. Okay, let's array these around. Hold on a minute. Let me just extrude these. And we'll array these around. Okay. Now I'll go select this diffuser and I'll do a Boolean subtract on it and grab those suckers. And voila, now we have a disc with a bunch of holes in it. Okay, now this is what I wanted to show you. Okay, when this disc, and keep an eye up here, when this disc, is in flashlight mode, it's going to be around the LEDs like that, so they poke through this thing. Probably not quite that far down, but probably something like that. But again, they have narrow cones, so the light actually kind of protrudes out of almost the tip of the LED, not quite, but almost. So the point is that all LEDs would be available in flashlight mode. Now when you have it in candle mode, you'll raise, remember this diffuser is attached to the tube there, you'll raise it, and then the have a little track on it that allows you to slip it out of phase like that. Okay, so the holes aren't exactly aligned with the LEDs. That's the whole idea. So it'd be like that. So it's completely out of phase, but that means that an LED under here, for example, its light will hit this part of the disc where there's no hole in it and deflect off and reflect off. But again, remember these LEDs have a viewing cone to them, so there's really it's modeled as a 55-degree off-axis cone of light. So like this LED, the higher this disc is, like if this disc were up here, in fact let me go ahead and draw you a cone if I can. Let's see, I think it'd be better done with this. No. Yes, I can't get the I need to draw a precise angle. I've done that before. Don't have it in here. Trying to think of the easiest way to go about this. I guess this would be the easiest. Okay, so this is going to be the draft angle, so it's going to be 1/2 of 55 degrees, so 27.5 degrees. That's our draft angle. But it's got to be negative, so minus 27.5 degrees. Okay, so basically, let me go create a cones layer, move this to it, and go ahead and change the color of it a little bit. Okay, now if I center this cone on one of these LEDs here, you can see, even by the side there, let alone what I'll do here, that if it's right here, you can see where the cone of light is actually coming through it. So you can see that basically through this hole here and this hole that's under here, some of the light would be leaking through. So that'll actually create little spotlights that kind of shine up on your ceiling, when it's in diffuser mode, particularly coming from our all-important middle LEDs. But again, what I may end up doing is, instead of using the center LEDs, is use the side LEDs, for the candle mode. But the problem is that, if I put, seriously, if I put one of these cones here, it tends to kind of bleed off to the side, which also creates not just shadows on your ceiling, light spots on your ceiling, but also makes your diffuser look almost dark when you see the shadow of it on the ceiling, when it really isn't dark. It just makes it look darker than the little light spots that peek through it. But again, that's one of the things that dictates how high this diffuser should ultimately be when it's in candle mode. But if you bring it down a little bit, you see how this cone now is more captured. So there's going to be a brighter spot on the disc, but it's not as inclined to bleed off the side. So that's what's going to dictate our ultimate travel on the constraint of our ultimate travel on that is how, as far as how high we want that diffuser to raise, would be, a combination of either using this LED for LED candle, or using this one for LED candle and making sure that it doesn't come through any holes. But see, even with it being that close, it'll still bleed through some of those holes. So that leads me to believe that the flashlight mode LEDs, the ones that are only going to be on if you have it set to flashlight mode, should actually be the middle ones. Whereas the candle LED mode, here, let me take this. Take this and stick it over here so we can look at both at the same time. Roughly center it. Anyway, the LED candle mode would best be there because none of the light will bleed through the holes, and if we leave the diffuser, make the diffuser so it goes no higher than this, then we won't have to worry about light bleeding off the edges too terribly much, as you can see here, because that's still the majority of the LED light, will be held here. There'll still be some side lobe radiation that will come off, even with the disc being that close, but still the vast majority of the light, will be within this 55-degree cone coming out of the LED. Again, there'll be some bleed off, but it won't be too terribly bright, and it'll be kind of at a very oblique angle. So the point is, with it being right where it is here, yeah, this would be therefore the maximum height we want that diffuser to be, to be raised to, when we travel up. So that's something, definitely to keep in mind. I'll just put a little line here too, to in case I end up forgetting about it later and accidentally moving this thing, which I might do. That would be the maximum travel, and here, like I said, right here would be the minimum travel, depending on where the top of our housing comes from. So it's not a very big distance there. In fact, I can measure that distance, you know, with the line. You can see right down there, it's about half an inch, about 465 mil. So it's going to be approximately less than a half an inch travel. So it's not a very big, not a very big amount of travel that we're talking about here, but it's enough to kind of keep everything nicely constrained. Now there is another consideration though, and this is a bit of an issue, that if we don't get this thing high enough, we may not have much light coming off the side of it, so we'll have to deal with that later, because that's one of the reasons I do this disc, is so that you get that back glow, so it's really almost a 300 plus degree illumination pattern coming off this. That's why I do this disc. That's the basis of my patent, in fact, or one element of my patent, in fact. At any rate, because we'll probably end up using these 3 LEDs here as our candle LEDs, and these will be the flashlight only ones, since they're so close to those holes. So, and oh, by the way, when this is in retracted mode, of course, it'll be actually twisted, obviously. But anyway, but the fact of the matter is that when that thing's up here, when our diffuser is up there, it's going to be because we'll have the base of our candle here, so any light hitting here will be able to bounce down, but there's going to be more of a shadow because it's not that high. That's why I was hoping to have this thing higher than this, but with those holes in it, I'm skeptical, But the nice thing about this is, though, is that since this really is a question of how long this tube is, I can actually have several different lengths of tubes to determine experimentally what the best height actually is in practice versus just playing around on CAD here, before I glue anything together. So I mean, so the point is that I'll leave that up to experimentation, but this is still going to affect our travel, though. So it's not just a question of the tube, because it's going to really be a serious constraint on our travel path and what kind of path I put in there. So I really can't change this later in experimentation. So and like I said, this is, this may be confusing to you, but it's part of the design process. I mean, these are the decisions you make. I mean, you try to explore what-if scenarios, like, oh, well, maybe I can just, modify the tube in practice. Well, yes and no. I mean, I can't, because I've already printed the housing, and I got to have this track in it that this little ring that we drew earlier, is going to slide along, because I got to have 3 little guides in it. Like one here, and one here, that go on a track that we've 3D printed at the side of our housing, so that it can actually follow that track and stay, raised when we raise it. Another alternative is I actually could have several track positions, but still, that's a little different. It'd be probably a little tricky to pull off. I don't know if that'd work, because I don't think because it's going to be a little bit difficult just to print a track like this with a 3D printer. So, I got to keep these things in mind. And again, you'll see as we get into this what I'm talking about. That again, this comes with a little experience, that you start thinking about what your 3D printer can and can't print, and you start realizing how that affects your designs and how you go about things. Now, like I said, if I had a 3D printer with a dual head attachment on, I could print those water-soluble support structures, I'd be much more in favor of doing that. But even if I had my printer dialed in, I mean, you know, that can be a mess trying to clean those damn support structures off, you know, when you do overhung prints. So again, that's why I still try to just take my 3D printer at face value and what it can and can't print, and I use that as an additional set of design constraints on what I do here. And a lot of times you'll find that those same constraints are also constraints when it comes to injection molding, although sometimes they're not. So, but that's where you you know, you print out objects that have more than one half to them. You know, you take a part that is like has detail on top and bottom, and you cut that in half basically, and you print the top and the bottom independently, and you glue them together. So that's how you get around that. You know, it's the easiest way to get around it. And you will see, well, you might see an example of that with this. I don't know. Let's see. So what do I need to do? Yeah, well, anyway, let's get back to our ring, because like I said, that can still be finished up irregardless of what the outcome of the other is. Now when it comes to this ring, okay, we need those little guides that I mentioned. Now the guides, let's see, I think I want, but again, this is sort of arbitrary. I don't want to make them too wide, but I want to make them so small they might break off. You know what I mean? I'm going to keep them to say 0.3 inch, and then, you know, we got our constraint there, so I'm going to go to like 120 mil height, 0.3, and close it. Okay, now since this is going to be a guide and this is going to slip through a track, I want, and remember, when we print this ring here, this is going to be the first layer. This is going to be the last layer, so it's going to print up. So basically, there's no constraints on printing up, but printing down, I got to pull a chamfer here, and I'm going to set that to, let's just start with, say, 50 mil and see how that looks. Okay, that'll probably be fine. Okay, well, let me go set this back to 0, 0. So I'll always use it 2 square corners off. Now let me go do a fillet on top, because you know, on the bottom, since we're 3D printing from the bottom up, 45 degrees is a safe angle. We don't need supports for 45 degrees or greater. So if that was like 80 degrees or 85 degrees or something, we don't need supports, and 45 is safe. And I think it can go a little shallower than that, but I know there's a limit, because at some point it's trying to print in free air. You know, you got filament, you know, this nozzle extruding filament in a downward direction is being pulled down by gravity, and if that angle is too shallow, you know, the filament will start to not stick right, and will start, you know, producing a really rough surface and so forth. It just doesn't work well, because it's trying to print in mid-air is what it's trying to do, and we don't want to do that. So but I know I can safely get away with a 45 degree angle. And okay, on the top, you know, we're going to want to fillet distance, you know, because I can fillet the top, you know, but I had to chamfer the bottom for that reason. But let's stick with say 0.04. You know, so that can be rounded, because I'd like the bottom to be rounded too, but I can't. You know, it'll produce a kind of a rough surface. I'm going to get away with it to some extent, but you know, it's better just to be aware of that. But you know, when this is traveling through a track, I want it to have smooth corners, so it's not as inclined to get stuck on something. So you know, because remember, this piece here is going to actually end up traveling through a track. So anyway,